thought it would be valuable to just do a couple of examples of working with function notation just to make sure you're clear on how these things work. So in this particular question, we're told that a function f of x is equal to 3x squared plus 1, and we're asked to find f of 1, f of minus 3, and f of 0. Now this is just a shorthand way of asking what would typically be a basic substitution question. So if I wanted, I can work out f of 1. F of 1 is going to be this expression with the x replaced by a 1. So in this case, I'm getting 3 times 1 squared plus 1. 3 plus 1 is 4. If I want to substitute in minus 3, I can write that as f of minus 3. If I work that out, putting minus 3 in, I get this expression. Minus 3 squared is 9. 3 times 9 plus 1, 27 plus 1, or 28. And finally, if I want to work out f of 0, I get 3 times 0 squared plus 1. 3 times 0 squared is still 0. This is going to be 1. So this is kind of the most basic thing you would use function notation for. It just makes showing substitution a really quick and easy process. Instead of me having to say, this is what y is equal to and x equals 1. This is what y is equal to and x equals minus 3. It gives us a short, sharp, easy way of referring to the results that I get here. So I would say that f of minus 3 is equal to 28. F of 1 is equal to 4, and so on. Just makes it nice and easy to refer to those results from a substitution. Second example I've got here is a proof one. This one's a little bit nasty because it involves algebra, and I'm asked to show two things about this function. I'm asked to show that f of a is the same as f of 1 on a, and then after that I'm asked to show that f of negative a is equal to f of a. So we can do these one at a time. I'm going to do part A first. It's a proof, so I have to show that the left-hand side is equal to the right-hand side. So I'm going to start by working out what f of a is. Now in this particular case, I'm just going to replace all the x's with a's. So f of a, that's a squared plus 4 plus 1 on a squared. It's nice and easy. F of 1 on a, well, I can work that out by putting 1 on a in everywhere I see an x. So this is going to be 1 on a all squared plus 4 plus 1 on a all squared. Now I'm going to have to use my index laws here. 1 on a all squared is the same as 1 squared on a squared. 1 on a all squared is 1 on 1 squared on a squared. The 1 squareds are just 1, so I'm going to get 1 on a squared. Here, I'm going to still have a 1 here, but I've got a division by a fraction divided by a fraction. I have to rewrite it like this. I can write it as 1 divided by 1 on a squared. If I'm dividing two fractions, I switch it to a multiplication and I flip the second fraction. Okay, that should all be in brackets. So I get 1 on a squared plus 4 plus this ends up being a squared, and that is in fact f of a, just in a slightly different order. So this is equal to f of a, and I have shown my result. For part B, and to do this, I'm actually going to slide that down. Oh, and it's not letting me do it. There we go. For part B, I'm showing a similar thing. I'm showing that f of minus a is the same as f of a. We already saw that f of a was equal to x squared, not x, a squared plus 4 plus 1 on a squared. Working out what f of minus a is, I get that this is minus a all squared plus 4 plus 1 on minus a all squared. When I square a negative, it becomes positive, so I get a squared plus 4 plus 1 on a squared, and that is the same as what I had before, and I have proven the result in this particular case.